All right, so for the rest of today, we're going to get started on section 1.4. We're not going to finish it. Like I said, it will be finished on Friday in class, and we'll have the homework for it due on Monday as well as a quiz on Monday. This section talks about what happens when you're looking at continuity and then at limits that are specifically one-sided. And we've looked at one-sided limits before and talked about those from a graphical point of view and a numerical point of view, like tables, but we haven't talked about what happens from an algebraic point of view with one-sided limits. So to start with, we're going to talk about continuity. So continuity at a function f, or a function f is continuous at a point c when the following are true. It has to be defined, so you can't have an open circle only at that point. So we've talked about places in the last lesson where I was like, oh, what's happening here is that we have an open circle, right? We have a hole in the graph. No holes in graphs. That's not going to work. Secondly, the limit has to exist. So what does that mean? Well, it means that the value from the left and the right have to match, which means there can't be a jump. Okay? And then the third thing is that the function value and the limit value have to actually meet. So what you can't have is you can't have the limit approaching this open circle here with a dot, a function value here, which technically you could have if you only had the first two pieces of this, is that you could have this image going on. Okay? So that's a no-go, right? Because the function value and the limit value are different. Okay? Continuity from a intuitive perspective. You've probably thought about this before, kind of like this, is can I draw it without picking up my pencil? Have you thought about it like that before? It's a common way to do it. Obviously, it's going to avoid the jumps. It's going to avoid the holes if you think about it that way. So from an intuitive perspective, that works pretty well. We have continuity at a point. That's what this actually says, at that very specific point on my graph where that hole and the filled-in circle don't meet up. It's not continuous. But sometimes we don't just want to know, is it continuous at one particular point? We want to know over an interval, is it continuous? And so this one says that if you're talking about an open interval, a function is continuous when it's continuous at each point on the interval, which seems reasonable, right? If it's continuous all throughout the interval, it's going to be continuous at each point in the interval. And if it's continuous on the entire number line, negative infinity to infinity, then we say it's continuous everywhere or everywhere continuous. Okay, so that's a little bit about continuity. We'll get into a couple more questions about it later on. I want to shift gears then and talk about what we do when we're talking about one-sided limits. Now, when we talked about one-sided limits from a graph, we talked about sort of drawing this sort of a path that we're following from the left-hand side or from the right-hand side, right? When we looked at graphs or looked at one-sided limits from a numerical perspective, we said, okay, well, we only want the values that are slightly bigger than 3, or only want the values that are slightly smaller than 3, and we compared only those values. The wonderful thing when you're talking about algebraic limits and one-sided limits is it works just like it does if you were talking about two-sided limits. So if you can plug the number in, you're good to go, and you just do it. You plug the number in, okay? And you can do that on this one, right? This is the limit as x approaches 8 from the right. There's absolutely nothing that prevents me from putting 8 in for the x, and so that's exactly what I do. And when I plug in 8 for x, I get 1/16. It really is just like that. It's good stuff. Of course, it doesn't always work. If I try to plug the 9 in here, again, the negative after it doesn't do anything in terms of calculation, right? It just tells you it's from one side. What will happen if I try to plug 9 in here? Yeah, the denominator is 0, and the numerator is 0 as well. The fact that the denominator is 0 tells me I can't do it. The fact that the numerator is 0 and the denominator is 0 both tell me that I stand a really good chance at simplifying this in some way where I can actually find an answer, okay? So this is one that's an example that I sort of started talking about in 1.3 as we were overviewing it, but it didn't finish. I have a radical, right? So I need to rationalize and get rid of that radical where it is, because if I do, I might be able to simplify things in such a way that I can evaluate and plug in the number. So that's what we're going to attempt to do. So what we need to multiply by is what's called the conjugate, as I mentioned. So what would the conjugate of this numerator be? Right, the square root of x plus 3. Now with the numerator, that ends up meaning I multiply my first terms together to give me an x. And I multiply the last terms together to give me a 9. And what sign goes in between? A negative, because one was a positive 3 and one was a negative 3. It's tempting sometimes when you're doing algebra to just start multiplying things out. When we're working with rationalizing, that's not a helpful approach. It's much more helpful to keep the pieces separated as factors, like this. And as I mentioned before, until I plug in the 9, I need to keep rewriting the limit as x approaches negative 9 from the negative side. Do you see something lovely? Yeah. So, and this is why I don't want to distribute, right? This is why I don't want to multiply things out. It's because lovely things happen. That's the whole point of multiplying by the conjugate, is something's going to cancel out. And if I start multiplying it out, it becomes really difficult to see where that cancellation was supposed to happen. But if I leave it in factored form, it's still there. So please remember, you still have a 1 on top, right? Cancels to give you 1. And on bottom, I now have the square root of x plus 3. And I still have the limit as x approaches 9 from the left. I do still have a square root, but because there's an addition fact instead of subtraction, I'm able to actually evaluate it. So what happens when I put in 9 here? Well, first of all, I don't need to write limit anymore because I'm actually finding it. What's the square root of 9? 3, plus the 3 that's already in the denominator, so I get 1/6. All right. The next problem requires a little bit of setup because their absolute values do things a little bit funny. So I think we'll stop there for today and we'll pick back up on number 3 when we meet again on Friday.